Welcome class 11th. Here in this part, I am going to start a topic, emission spectrum of hydrogen atom. Now, as we are dealing with the structure of atom, so the spectrum of hydrogen atom played a very important role in the development of atomic structure. Now what happens? The spectrum of hydrogen atom can be obtained by passing an electric discharge through the gas taken in the discharge tube under low pressure. The spectrum of hydrogen which was observed, that was obtained basically by passing an electric current through a gas which is present in a discharge tube, and that gas which is present in a discharge tube has very low pressure, which is filled under very low pressure. So as the light beam or the electric current or the electric discharge is passed on that glass tube or that discharge tube which has gas in it, what happens? We got, or the scientists got, the structure of the spectrum of hydrogen atom. And the emitted light, the lights which was emitted by that experiment, by that tube, those emitted light is analyzed with the help of spectroscope. Spectroscope is an instrument with the help of that spectrum or the emission of that light can be analyzed. And the spectrum consists of a large number of lines. That particular spectrum which was analyzed by the spectroscope, that consists of a large number of lines which are present in different regions, which are present in different region of wavelengths. जो भी लाइंस उस स्पेक्ट्रोस्कोप की हेल्प से जो स्पेक्ट्रम की लाइंस आई थी, that lines have different wavelengths in which are present in different regions of different wavelengths basically. So these lines in different regions were grouped into 5 different series of lines. वही जो lines different region में present थी उन्हें फिर grouped किया गया into 5 different series of lines. And the 5 different series of lines are, first is Lyman series, Balmer series, Paschen series, Brackett series and Pfund series. These are the 5 lines which further 5 series which further grouped when the lines are grouped in 5 different series. So these are 5 series. And as the series of hydrogen spectral lines were discovered, then there is a general expression of the wavelength with that particular line was there, and that equation is known as RYDBERG equation. So let's see. This is the RYDBERG equation in which the wavelength 1 upon lambda is equal to r into 1 upon n1 square minus 1 upon n2 square. And this will also be equal to wave number. Since we know that 1 by lambda, inverse of lambda is equal to wave number. So this is also equal to wave number, and the unit for this equation comes to be centimeter inverse. Because it is inverse of wavelength, so the unit comes to be centimeter inverse. And here n1 and n2 are integers. And it should be noted that n2 should always be greater than n1. Now r is constant. This r is constant here and it is known as RYDBERG constant. The value of r is 109677 centimeter inverse. This is found to be valid for all the lines in the hydrogen spectrum and is also known as RYDBERG equation. So after the discovery of different series of hydrogen spectral lines, this expression was discovered by RYDBERG. Limiting line. The limiting line of a spectral series, of any of the spectral series in the hydrogen spectrum, is the line when n2 is equal to infinity. From the RYDBERG equation which we have discussed, from the RYDBERG equation, if the value of n2 becomes infinity, then we got the special type of line, and the line is known as limiting line. And that line, this line will have the shortest wavelength, because we know that because our Rydberg equation is 1 upon lambda. So as the value of n2 is infinity, so we got this line of shortest wavelength and the largest wave number. So this is known as limiting line. Now let's see different spectral lines in the spectrum of hydrogen atom. As we have discussed that there are 5 series of hydrogen atom, and the Lyman series, the reason for Lyman series is wavelength reason for Lyman series lies between ultraviolet, it is ultraviolet region, and the value of N1 is 1 for Lyman, and Balmer and value of N2 for Lyman series it will be 2, 3, 4 or 5 and so on up to infinity. Similarly for Balmer series, the region is visible region and the value of N1 is 2 and N2 will be 3, 4, 5 and 6. Here you can also see that the value of N1 will remain constant for all the series. All the spectral series, the value of N1 will remain constant, but the value of N2 will get vary. It will be varies, and for Lyman series you can see that N2 will be this 2, as N1 is 1, so N2 is 2, 3, 4, 5, and we can also say that N2 can be N1 plus 1, it can be N1 plus 2, 1 plus 2 is 3, 1 plus 1 is 2, 1 plus 3 is 4. So similar, these N2 for any series it can be varied, but the value of N1 for any of the series will remain constant. Come to the Paschen series. The reason for Paschen series is infrared. N1 is 3 and N2 will be N1 plus 1 and so on. So it is 4, 5, 6 and 7. And Brackett series, the reason of Brackett series is also infrared reason, and the value of N1 is 4, but the value of N2 will be 4 plus 1, N1 plus 1, 5, N1 plus 2, N1 plus 3 and so on. And the last series is Pfund series, and the reason for Pfund series is also an infrared reason, and the value of N1 is 5, it is constant, it is 5, and N2 is 5 plus 1, N1 plus 1, 6, 7, 8 and 9 and so on. So this is the spectral line and the different reason in which that spectral lines lies. Now you can see the different series in this image also. For Lyman series, as we are talking about Lyman series, the reason for Lyman series is ultraviolet, and the value of N1 shell number for Lyman series is 1. It is K shell, and all the lights, all the emission which are from n equal to infinity shell, they will all fall to the n equal to 1 shell. Since you can see here, this emission is from n equal to infinity, it will be fall to n equal to 1, and n equal to 7 to n equal to 1 again, and similarly from n equal to 5, 6, 3, 2 to n equal to 1. So for Lyman series, n1 will be 1 and n2 will be 2, 3, 4, 5, 6 and so on up to infinity, as we have discussed earlier. As we come to Balmer series, we know that Balmer series falls to the region of visible region, where the wavelength of light is in visible region. So for Balmer region, N1, value of N1 is 2. It lies in second shell, or we can say that it is in L shell as well. So all the lights which is coming from the infinity, they will fall up to the second n equal to 2 shell, second shell. Now come to the Paschen. For Paschen series, n is equal to 3. So all the light which is coming from the infinity, they will fall in n equal to 3 region, and the Paschen series will come in infrared region and infrared region of near infrared. We have two type of infrared region. One is near infrared region and other one is far infrared region. Near infrared region means the region which is closer to the visible region, and the far infrared region means the region which is away from the visible region. That region is known as far infrared region. So Paschen falls on near infrared region because it is closer to Balmer region, and similarly Brackett series will fall towards far infrared region because it is much far away from Balmer region, and because Balmer is falls on visible region, that's why Brackett is far infrared. And we know that for Brackett the value of n1 it is 4, and come to the last series, that is Pfund series, and the value of n1 for Pfund series is 5. So all the emission will which were coming from the infinity, they will form up to only fifth shell. So this is the spectrum of hydrogen, line spectrum of hydrogen atom, in which the series are presented in the line form. Also, it may be noted that the RYDBERG equation is true only for the spectral line of hydrogen atom and the hydrogen-like ions. RYDBERG equation, which was discussed earlier, that is only true for the spectral lines of hydrogen atom and the hydrogen-like ions. The hydrogen-like ions are those ions which contain only one electron. As we know that hydrogen atom has only one electron, so the ions which has the same nature as hydrogen means hydrogen-like ions means they will also contain only one electron. Those ions which will contain only one electron, they will only show, or they will only be true, the RYDBERG equation only be true for such type of ions which have only one electron, like a hydrogen atom. So the examples are like helium ion, He positive, Li2 positive ion, lithium ion. Since we know that atomic number for helium is 2 and helium has 2 electrons, and as helium loses one electron, so one positive charge will be there in helium, and since helium initially has 2 electrons and it loses 1 electron, so only 1 electron will be there in helium and it will get a positive charge. It will become a helium ion now. So it means now as it has only 1 electron in helium ion, so helium ion is also behaves as hydrogen atom, so it will give the spectral line as the hydrogen atom gives. Similarly, as we are talking about lithium, since as I talk about lithium ion, so lithium ion contains 3 electrons basically, and as it contains 3 electrons, and here as the 2 positive charge is present on lithium ion, so it will loses 2 electron to lithium 2 positive means lithium ion will have, it will loses 2 electron and now it will have only 1 electron in it. And as lithium 2 positive ion has only 1 electron in it, it means it is much similar to hydrogen atom which has only 1 electron in its atomic form. So these are the examples of ions which behaves like helium, hydrogen atom, because they have only 1 electron. And the RYDBERG equation for such type of ions will be 1 upon lambda is equal R into 1 upon n1 square minus 1 upon n2 square into z square here. And where this z is nuclear charge which is equal to atomic number and R is the RYDBERG constant. This must be noted that here this z is atomic number or the nuclear charge. As I am talking about helium ion, He positive, so the atomic number for helium is 2. Atomic number of helium is 2. So here you have to write in place of z, you have to write 2 square for helium. If we have to calculate spectral lines for helium ion, so in place of z in RYDBERG equation you have to write 2 square. And similarly, if we have to find out the spectral line for Li2 positive ion, and we know that the value of z, the atomic number of lithium, is equal to 3. So for if we have to calculate the spectral lines using RYDBERG equation for lithium ion, so in place of z here you have to write 3 square for lithium ion. So here this z will represent atomic number of that particular atom which is which will behave on losing electron, which will behave like hydrogen ion. It means on losing electron which will have only 1 electron. So that's all for today, and we will meet with our some next topic in our next videos. So keep watching. Thank you.